Welcome to the presentation on Input-Output Systems Overview. We will explore the fundamental aspects of input-output systems, focusing on their hardware and software components. Input-output systems are the crucial link between the computer and the outside world, facilitating the transfer of data. Here are some of the key components that we will be discussing, including storage devices, display units, printing devices, and various connecting interfaces. Let's delve into the key components of input-output systems. Firstly, let's look at the hardware components. These include various input-output devices such as disks, printers, and network interfaces. Next are the device controllers, which manage the interaction between the input-output devices and the system. Input-output ports and buses provide the physical pathways for data transfer. Direct memory access, or DMA, controllers enable devices to access memory directly, and finally, input-output channels and input-output processors handle more complex input-output operations. Now let's explore the software components. Device drivers are essential for translating operating system commands into device-specific instructions. The input-output subsystem kernel manages input-output requests and resources. User space input-output libraries offer application programming interfaces for easier input-output operations. Buffering and caching enhance performance by managing data flow, while spooling and device reservation handle device sharing. Finally, error handling mechanisms ensure system reliability. Here we have a simplified diagram of the input-output system architecture. At the top, there are the user applications which initiate input-output requests. On the left, there are device controllers which manage the physical devices. At the center, we have the operating system's input-output subsystem, coordinating all input-output operations. On the right are the device drivers, which translate generic commands into device-specific instructions. And at the bottom are the actual hardware devices, such as printers, storage units, or displays. The interaction between these components forms the core of the input-output system. Let's take a closer look at the device controllers, which are essential hardware components that serve as interfaces between the main computer system and input-output devices. Device controllers contain registers for data, status, and control information that the central processing unit or CPU can access. Some common device controller registers include the data register for data transfer, the status register for device status, the control register for control commands, and the error register for error information. These registers allow the CPU to manage and monitor the input-output devices effectively. Now let's discuss the different methods of input-output communication. The first method is programmed input-output, where the central processing unit or CPU directly controls the input-output operations. The second method is interrupt-driven input-output, where the CPU initiates the input-output operation, and the device signals completion via an interrupt. The third method is direct memory access, or DMA, where a special hardware transfers data between memory and the input-output devices without CPU intervention. Here is a brief comparison of these methods. Programmed input-output has high CPU utilization, low complexity, and is best for simple devices. Interrupt-driven input-output has medium CPU utilization, medium complexity, and is best for interactive devices. Direct memory access has low CPU utilization, high complexity, and is best for high-speed transfers. Let's examine direct memory access, or DMA, in more detail. In a direct memory access operation, the central processing unit, or CPU, configures the DMA controller with the transfer details. The DMA controller then manages the data transfer between the device and the memory, while the CPU continues with other tasks during the transfer. Once the transfer is complete, the DMA controller interrupts the CPU. This significantly reduces CPU overhead for large data transfers. Here is a simple diagram illustrating the direct memory access architecture. The CPU communicates with the DMA controller, which in turn manages data transfer between a device and the memory. Now let's delve into the different layers of input-output software. These layers include user-level libraries, which provide simplified interfaces for application developers. There is also a device-independent operating system layer, which handles naming, protection, blocking, buffering, and allocation. Device drivers are also included, which are device-specific code that communicates with controllers. Finally, interrupt handlers are used, which manage device interrupts and initiate driver operations. Here is an example of system call, where the user-level file read operation calls the system call to the operating system, which then calls the appropriate device driver. Let's explore some techniques to optimize input-output performance. One technique is buffering, which stores data temporarily in memory to accommodate differences in device speeds and data transfer rates. This reduces the frequency of physical input-output operations. Another technique is caching, which keeps copies of frequently accessed data in faster storage. This improves performance by reducing access times for repeated operations. Spooling is yet another technique, which queues output for devices that cannot accept interleaved data streams, allowing multiple processes to generate output for the same device. Finally, input-output scheduling reorders input-output requests to minimize seek times and maximize throughput, which is particularly important for disk operations. Now let's discuss how to handle input-output errors and recover from them. Common input-output errors include transient errors, which are temporary failures that may disappear when the operation is retried, permanent errors, which are hardware failures requiring repair or replacement, data transfer errors, which is corruption during transmission detected by checksums, and device timeouts, where the device fails to respond within the expected time frame. Some error recovery strategies include retrying operations for transient errors with exponential backoff, using error correction codes to detect and fix data corruption, implementing redundancy through mirroring or RAID for storage devices, checkpointing and journaling to recover from system crashes, and graceful degradation when full functionality cannot be restored. In summary, input-output systems bridge the gap between the central processing unit and external devices. Hardware components include controllers, buses, and direct memory access. Software layers provide abstraction and device independence. And performance optimization can be achieved through buffering, caching, and scheduling. Looking ahead, some future trends in input-output systems include non-volatile memory express and storage class memory, persistent memory programming, computational storage, and hardware-level security. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.